Okay, so if geothermal power is so good, why isn't everybody doing it? Well, let's talk through some of the challenges. One challenge is the low Carnot efficiency of electric generation. We'll talk about that in a second. Second challenge is heat transfer to the underground pipes. And then how do you drill deep and cheap? Because you'll see the solution to these require that we drill large numbers of holes to very great depth. So unless we can do that cheaply, we're in trouble. So basically it all boils down to cost. Can we actually get competitive costs in terms of dollars per megawatt hour from geothermal power? And at the moment we can't. So let's talk about the first problem, the Carnot efficiency. Now if you remember, Carnot limit applies to heat engine. And what a heat engine is you get a reservoir of hot stuff and cold stuff, and you let heat flow from hot to the cold, and by some mechanism in between, like a turbine or a steam engine or something like this, you convert some of this heat difference into useful energy like motion or electricity. And Carnot showed that at most your efficiency is 1 minus the temperature of the cold reservoir over the temperature of the hot reservoir, and that's the highest possible efficiency you can get with any heat engine, converting heat temperature difference into electricity. So let's try that out for geothermal power. So let's imagine you drill a hole 1 kilometer down. That's a pretty big hole, 1 kilometer. And let's imagine the temperature on the surface is about 15 degrees centigrade, 288 Kelvin, which is the typical sort of Earth's surface temperature. Temperature at the bottom will be 15 degrees from the top plus the 25, because the temperature on average goes up by 25 degrees per kilometer. So we're assuming this is just a typical place on Earth, nowhere special, not chosen to have hot volcanic springs or something underground. So that means we've got 288 Kelvin as our cold temperature, 313 Kelvin as our hot temperature. So now if we plug this into the efficiency equation, you get 1 minus T cold over T hot, so it's 1 minus 288 over 313, which comes out as 8%, 0.08. Awful. So what that's telling us is if you drill a kilometre deep hole, the water coming up is going to be at about 40 centigrade. That's quite hot water. But if you want to turn that into electricity, that's going to be very, very hard, because only 8% at most, and probably less than that, probably more like 5% in reality, will be converted into electricity, and most will just stay as heat. So if we want to get electricity from a geothermal plant, we need to go deep, or drill in a place with hot volcanic springs just below the surface. So let's say we go down to 15 kilometers. That's a very deep hole. In that case, the temperature at the bottom is going to be about 390 centigrade, and if you plug that into this whole Carnot limit equation, we get 54% efficiency. So what this bit of physics is telling us is that to get electricity from geothermal power, we need to get the temperatures high, which will mean generally drilling deep. How deep and how efficient will depend on where you're doing it, but unless you go deep, 1 kilometer is not going to do it. You're going to have to go deep, and that's going to be expensive. Now, given these numbers, a lot of people think that geothermal power is actually not a very good way of producing electricity, because you have to go so deep and that's going to cost so much. Instead, why not use it directly for heat? Now, this is already very widely used. There are volcanic hot springs in onsen baths in Japan, for example, and many other places in the world, where you can swim in hot water that's come up from underground. So maybe this is a better use. So it's already used for spa baths. You get the water from underground, and that's nice and hot and full of minerals and things, and you can have a bath in it without having to use electricity to heat it up. District heating is used in many countries. Now, it's rare in Australia. Normally every house, every office has its own heating system. But in some parts of the world there are district heating systems that would supply a whole suburb or a whole complex of office buildings. And one way to do this would be to have a geothermal heat source, drill down, get some hot water up, and then use it to keep a whole suburb warm by pumping the water to all the places. And that's widely used in, for example, some of the colder regions of China and Russia. Or industrial process heat. If you remember, a large amount of carbon dioxide emission comes from industry, and a lot of that is heating things up. As for example, paper making. You have to heat up the paper pulp enough to several hundred degrees. Now here is a graphic produced by the Geoscience Australia showing what sort of temperatures you need to do various things. So for example, if you have 30 degrees centigrade hot water, that's warm water for mining in cold climates for de-icing fish farming. If you go up to 90 degrees, you can dry stock fish in intense de-icing. Dry and cure light aggregate cement slabs at 110. Digestion of paper pulp at 180 degrees C. Down here you've got hot water. Up here it's saturated steam. But nonetheless, there's a whole range of temperatures where if you get hot water coming out of some hole in the ground at these various temperatures, depending how deep you drill, you can actually use it for a whole lot of industry. You're not producing electricity, but you're saving a lot of electricity or gas that would otherwise have to be used to do this industrial process. And this way, you don't lose that Carnot efficiency. You don't have to drill so deep, like getting 30 degrees, but only need half a kilometre down or something like that. So nothing like as deep a hole. One thing that's actually been used in some places around the world is to combine geothermal power with heat pumps. Let me remind you about a heat pump. So heat pumps use the Carnot limit in reverse to heat up buildings. Now remember, a normal heat pump, you've got a hot reservoir and a cold reservoir, and the heat flows from hot to cold, and a small fraction of it produces electricity in reverse. Heat pump works the other way around. You get cold to hot, and the heat flows the other way, driven by the heat pump. So you might get out in the cold, you might get a fan like this. Inside, you might get something like this, and the heat pump in between that takes it from one to the other. So consider a Canberra winter night. Temperature outside about 0 centigrade, and you want temperature inside maybe 20 centigrade. So the Carnot efficiency, if you wanted to use the heat inside minus outside to get electricity, you'd only get 1 minus 273 over 293 is 7% out. So it's very inefficient. So I wouldn't try and use the heat in your Canberra house to get electricity. This is how a normal heat engine works, like a turbine or a steam engine. You get inside where it's hot, outside where it's cold. The heat flows. You get 100 watts coming in into the heat engine. 93 goes outside as heat leaking out, and 7% will go and produce electricity. But that's a heat engine. A heat pump does the whole thing in reverse. What you're now doing, because these things are basically reversible processes, is you get 93 watts coming in from the outside, plus you add 7 watts of electricity, and that gives you 100 watts coming into the house, which is why heat pumps are so efficient. With only 7 watts of electricity, you can get 100 watts of heat. So a heat pump is basically a heat engine generator run in reverse. Not all generators can do this, but a lot of them can. And electricity is used to move heat from cold to hot, not create it, and as a result they can be well over 100% efficient. In principle, as seen, it could be you get 100 watts of power for only 7 watts of electricity. No real heat pumps are that good, but most of them can give you 4 watts of heat for every 1 watt of electricity, and the most expensive premium ones can manage 6 watts. But they have a problem, and this is where geothermal can come in. Getting enough heat to the outside of the heat pump without noisy fans or the whole thing icing up. Remember, you've got one of these on the outside, and if it's a cold, frosty day, you've got to get enough air through this to bring in the heat and not have the whole thing covered in ice. So one idea is you turn your heat pump on its side, and you have the outside underground. This is called a ground source heat pump. And the basic idea is that while the air outside might be at 0 centigrade, the ground, even a few meters down, will have a much more stable temperature. It won't get as cold in winter, and it won't get as hot in summer. So what that means is, if it's, let's say, 10 degrees on the bottom, and you want 20 degrees inside, that means your Carnot efficiency is even less than 7%, which means your heat pump can work really, really well. And also, by having this in the ground, it's not likely to freeze up, and the heat can be transferred to the ground, especially if the ground has got some water in it. It could also be used in summer to cool things down. In this case, you're taking the heat out from the building and putting it into the ground. But once again, the ground's a nice steady temperature, so you can get very high heat pump efficiencies.